Alright, so we're taking a look at the Woodrowhoff algorithm for the linear network, and I'm trying out this TGF example from the book. And so I've got the two T's, two G's, and two F's here. And let's see, I think I've got it set up so that we can plot the data and see what it looks like. So let's go ahead and copy that. I thought we could execute it from here, but I'll just copy and paste. So I'm switching over to Octave right now, so let's paste that in there. Good. And I need to execute that. There we go. Good, so you see the same figure in the book. Now I should mention, what's interesting about this example is that translating letters like this forward in X really makes them difficult to figure out if they're the same letter or not. What I mean by that is, I'm just showing, okay, if you were to take like the Euclidean distance between these two matrices, do you see that they would be completely different? Even though in the whole, if you look at these holistically, right, this is the letter T and this is the letter T shifted. So these two things should be close together. But a translation like this, if you take the measure of similarity to be Euclidean distance, it's going to be awful. Okay, but that's neither here nor there for now. We may run into this issue later for other neural nets, but for now this is just our input. And what I'd like to do is I would like to distinguish between these letters. And so what I'm thinking of is I'm going to map these 14 or 4 by 4 blocks, which would be R16 to R1. And the two T's, I think we said we are going to try to map to -60. Let's see, let's pull up our editor again. What was our T's? Oh no, actually, we're going to do something good. I changed this from the way I did it in the notes originally. Originally in the notes I was going to make the output equal to -60, 0, and 60. And the reason that's no good is because that induces a metric on these letters. For example, that would mean that F is closer to G than it is to T, right? If you map these F's to +60, G's to 0, and T's to -60. And you don't want that. You don't want to induce a metric unless you really want to say that F is farther away from T than it is from G. And so a better way to do this is to map T to like the three-dimensional vector 1, 0, 1. And then the G's would be mapped to 0, 1, 0. And then the F's would be mapped to 0, 0, 1. I'm going to change that in the notes. So you probably don't understand what I'm talking about then with the -60, 0, 60. Or I may just leave it. Okay, anyway, let's just go ahead and run this code and see what happens. So once we set up our X and our T, we're just doing some visualization here in lines 19 through 23. And then down here you see where we start. Alpha is 0.03, but actually in the Woodrowhoff algorithm I'm going to use something different, and we'll see how that works. This is number of epochs, number of points, right? And so we just use the Woodrowhoff algorithm, and then we take a look at the output. So let's see what happens when we run this. By the way, you'll see this magical approximation here. So I could actually take the alpha off. In fact, I did. Alpha and the number of epochs. I think I'm going to need the number of epochs though. Let's keep that in here. Well, yes. Let me pause for a second. I took out some code earlier. I think I need to put it back in. Just pause for 1 sec. Okay, sorry about that pause. So we were taking a look at some code here for the Woodrowhoff example, the TGF example. And so yeah, I went ahead and changed the code slightly because I wanted to try out using this value of alpha that was in the book. This is what MATLAB uses, and you'll notice that this is um, coming from 1 over lambda max, where lambda comes from the maximum eigenvalue of the Hessian matrix in the when you're looking at gradient descent. And so that is the optimal alpha. And so in this case, we need something that's slightly less, and that's why it's 0.99999 divided by the magnitude of x, because we know that if I look at the matrix XX transpose, the eigenvalue actually is X transpose X. I think I have that as an exercise. Anyway, so this Woodrowhoff, maybe I should call this. I'll call this Woodrowhoff 2 in the notes or in the web page, so that you can distinguish between these. So this is the Woodrowhoff version that's going to go with the TGF example. Okay, and so the TGF example again, I got the TGFs, I've got my T's, which are three-dimensional vectors. Yeah, and then the main part of the code, we just run the algorithm. So in this case, we're running the number of epochs up to 60, just to see how it works. We'll take a look at the error and see if we needed to do that. All right, let's just stop talking and start running. Okay, so let's go with TGF example. Good. So what are we looking at here? First off, those are our data points, and what you're looking at in figure 2 is the run. We had several passes through the data, right? I just recorded the first 6. I guess it's 6 points for 60 runs. And you can see the error drops. So I didn't need to take 60. I could have taken 20 epochs, and that would have been fine, plenty, in fact. Good. And so the error just drops right down to 0. Good. All right. And now when I took my output, the matrix looked like this. And so remember, e to the minus 12 is basically just 0. So our first two vectors are 1, 0, 0, 1, 0, 0. In fact, let me just put my t here so you can see. And we see that the first and second columns are good, third and fourth columns are good, fifth and sixth columns are good. And so we have matched the output, right? And so just so you see, here's our W and there's our B. So if you want to match a couple of numbers in your output to my numbers, you can see those there. But actually from this output you can see that it's really good. Okay. Finally, I just wanted to plug things into the confusion matrix. So I got a C at the end, and there again we see that everything was classified correctly. Of course, we're doing what we shouldn't be doing, right? We're testing the training data, but we only have 6 points. Okay, so think of this as a proof of concept. We know that the W's and the B's can be modified at least to get the training data. Whether it generalizes or not is another question. All right. Now what was important about this example that I really wanted to emphasize, because you might be realizing that we did not have to use Woodrowhoff in order to solve this problem, right? Because this is just a straight W times X plus B equals Y kind of thing, right? Well, so we could use linear algebra to solve this. What's important here is Woodrow and Hoff were looking for a a system of updating that was biologically plausible, and so this is the update that they got. And so let's see, where's the update again? There it is. And so this is the update that they're using. And again, I guess the only thing that might not be plausible here is this piece where we take t minus the error. Okay, and so that may be a problem with the biology. However, Woodrow and Hoff were able to build a physical machine that actually did this calculation, and they were able to train the machine to physically produce the right classifications. So that was back in the 60s, I think. All right, so we're just going to do this computer simulation. I'll put these scripts on the web if you want to play around with them. You can see from the name here that we're going to be taking a look at some other data. The iris data is here from our last exercise. We might try it with the linear classifier, and the breast cancer data is another one that's very interesting to see if we can find a linear classifier. So it has several, well, I'll talk about it later. I'm starting to ramble. I better get out of here. Okay, talk to you later.